Now, the Bohr model can be generalized into a neat expression that is available on your formula sheet. And this gives the energy of a particular electron energy level as a function of n, which is which energy level the electron is in, and also z, which is the nuclear charge, or atomic number. So for hydrogen, z is 1. For helium, it's 2, and so on. Now, this expression only actually works for hydrogen-like atoms. That is, atoms that only have one electron. So hydrogen on its own is fine, but for something like helium or lithium, you need to remove electrons to get them down to a single electron, or in other words, ionize those atoms, to end up with something the Bohr model can correctly predict the energies of. And the reason for this is the Bohr model doesn't take into account interactions between electrons, but it can correctly predict at least the energies arising from the interaction between a single electron and a nucleus. Now, although the Bohr model can be generalized to these hydrogen-like atoms, that is really the limit of its utility. The Bohr model does not correctly predict the energies when there are more than one electron around the nucleus, and it also fails to explain a whole bunch of interesting quantum effects. And it doesn't explain, or doesn't describe correctly, the shapes of the regions that the electrons actually occupy around the atom. Now, for all of these more detailed interpretations, we actually needed a new model, and that model is the Schrödinger model, which you're going to be learning about in the next few lectures.